We need to start today with a discussion about what it means to be a real number. So when we graph a number line, we call it the real number line, and we use the symbol of an R with two lines on the left. Okay? Real numbers include, like the counting numbers, 1, 2, 3, 4, 5, and they also include the negative counting numbers, like -8, -7, and so on. And then the fractions. And every fraction can be written as a decimal that either stops or it repeats. For instance, 1/4 is the decimal 0.25. And when we say stops, we mean there's an end to it. The decimals terminate at some point. So 0.25, and then we're done. But 1/3 doesn't do that. 1/3 is 0.3333, and that continues on forever. So we put a line over the 3, and we say that is a repeating decimal. And you could even have like 0.124124. That can be written as a fraction. In fact, all you have to do is divide this by 999. So if I had 0.6868 repeating, that would be 68/99. So you just take the repeating part and you divide it by however many nines you need to get to that point. Those are all rational numbers. They can all be written as fractions. But there's another set of numbers that can't be written as fractions. There is no fraction that's equal to them. Those are called the irrational numbers, and the most famous is pi. And up there on the wall, you see pi to a bunch of decimal places, and we use a lot of 5s, but we never have a pattern that repeats over and over and over. So that's called a non-terminating, it never ends, non-repeating decimal. Some more irrational numbers would be like the square root of 2. That goes on forever and never repeats. And there are actually more irrational numbers than there are rational numbers. If we were to line up all of the fractions and we were to line up all of the irrational numbers, the set of irrational numbers is way bigger than the set of rational numbers. But together, if we combine every fraction with every irrational number, we get the real number line. And every number you can think of is on this line. So we start at 0 and we go off in both directions forever. And no matter what point you pick, it will hit a real number. There are no empty spaces in the real number line. Okay? But there are some numbers that are not on the real number line. Okay? The ones that you already know of are infinity and negative infinity. And there is some argument about whether or not infinity is actually a number. But if it is a number, it's not on the number line. In order to be a real number, you need to be able to point to a spot on the line and say, that's where it is. If I had 1 trillion, does that fit on the number line? Yes. If this is 1, then we'd have to go a long way to find it. But we could find it. It exists. But infinity doesn't. And infinity is sort of more of an idea than an actual number, but it certainly is not on the real number line. So we say infinity and its negative counterpart are not real numbers because they're not on the number line. Okay? Well, there's another number that shows up every once in a while that's also not on the number line. And that number is the square root of -1. So what number times itself is -1? Well, 1 doesn't work. 1 times 1 would be 1, so that's out. What about -1? -1 times -1 is +1, so that didn't work. What about 1 and -1? They're not the same number. So up until now, we haven't had any way to figure out what the square root of -1 is. But we're sure it's not on the number line. And because it's not on the number line, it's not a real number. Now, it doesn't mean it's a pretend number. When we say it's not real, we just mean it's not on the number line. It exists, but it doesn't exist on this line. So, we refer to these as imaginary numbers. Okay, not fake, but if you have real numbers and not real numbers, we call it an imaginary number. And because it's the imaginary number, we name it I. So the square root of -1 is I. So whenever you see I in mathematics, it will never be a variable. I always means the square root of -1. So if I had the square root of -4, I can split that into the square root of -1 and, let me put it the other way. The square root of 4 times the square root of -1. The square root of 4 would be 2, and the square root of -1 would be I. Does that make sense? Okay. If I had the square root of -121, that would be the square root of 121 times the square root of -1, and I get 11I. Does that make sense? What about the cubed root of -8? Can you cubed root -8? Yes, because -2 times -2 times -2 is -8. So this one actually just gives you -2. All right. What about the fourth root of -16? Well, what times itself times itself times itself is 16? 2. And what if I make all of those negative? -2 times -2 times -2 times -2. It's still positive. So this one is going to be the fourth root of 16 times the fourth root of -1. This is 2, and this is I. Does that make sense? Okay. So what if I had this? 4 times the square root of -25. Well, that would be 4 times the square root of 25 times the square root of -1, which would be 4 times 5 times I, which is 20I. Does that make sense? Okay. What about this? The square root of -24. How would you do that? We need to factor 24 and see if there are any pairs, and then we'll pull those out. We'll also pull the I out. 4 and 6, 2 and 2, 3 and 2. Can I take anything out? A pair of 2's. So 2 on the outside times the square root of what's left, which is 6. Where should we put the I? Well, if I put the I right there, that's kind of hard to tell if the I is on the inside or if the I is on the outside, right? So instead of making it confusing like that, we always put the I after the number and before the square root. Okay? All right, what about the square root of negative 210. What goes into 210? 10 and 21, 5 and 2, 3 and 7. What can I bring out? Not nothing. Just the I. Everything else stays in, but the I comes out. So we take this negative and we pull it out to be an I, and we get I, excuse me, I times the square root of 210. Okay? All right, let's do let's do 5 times the square root of negative 72. We need to factor 72. 8 and 9. 2, 2 and 2. 3 and 3. What can I bring out? Set of 2's and a set of 3's and an I. So what's going to be on the outside? There's already a 5, so 5 times 2 would be 10, times 3 would be 30, and then the I, and then the square root of the only thing that's left, which is 2. Does that make sense? Okay, so any number that's attached to an I is referred to as an imaginary number. But what happens when we try to add real numbers and imaginary numbers? So let's say I had 6 plus 5i. This number is real, and this number is imaginary, and they don't mix. It's kind of like 6 plus 5x. They're not like terms. You can't put them together. And anytime you have a real number added or subtracted with an imaginary number, we call this a complex number. Complex numbers always come in two parts, a real part and an imaginary part. Now, technically, all real numbers are actually complex numbers, and all imaginary numbers are complex numbers, because you could do this. You could say 0 plus 4i. The real part is 0, and the imaginary part is 4. And then you could also say 3 minus 0i. But we don't usually say that. A complex number has a real portion and an imaginary portion. And sometimes, if there is an imaginary portion, we just refer to it as a complex number. So I'm going to be using the words imaginary and complex interchangeably. But in either case, this is considered one number. That is one complex number. It just has two parts, a real part and an imaginary part. So we are going to be adding complex numbers together. If I have 5 minus 8i, and I add that to 3 plus 2i, how do I add those? You just do like terms. So 5 plus 3 is 8. And negative 8i plus 2i would be negative 6i. Does that make sense? Okay. What if I had negative 3 plus 2i plus, plus 5 plus 4i? What does that give me? Negative 3 plus 5 is 2, and then 2 plus 4 would be 6i. Okay. 8 minus 3i plus negative 4 minus 6i. Let's change that to a 14. So 8 minus 3i plus negative 14 minus 6i. Well, I put the real portions together. What is 8 minus 14? Negative 6. And then negative 3 minus 6i? Negative 9i. Okay, does that make sense? Can I move on to the next one? Okay, you can also subtract imaginary numbers, complex numbers. So 2 plus 4i minus 5 minus 6i. You have to be a little bit more careful when you do these because it's actually 2 minus 5. So what I like to do whenever you're subtracting is get rid of this and move it on the inside. What happens when I move a negative from the outside to the inside? Everything on the inside changes. So that would be minus, and this would become a plus. So 2 minus 5 would be negative 3, and 4 plus 6 would be 10i. Does that make sense? Okay. This one is a subtraction problem. So I like to change this subtraction to a plus, and then I'm going to change both of these. Negative, negative. Okay. Now I just do 5 minus 6 is negative 1. Negative 3 minus 2 is negative 5i. Do we think we can handle those? All right. This assignment is going to take us 2 days. So we want to do, in 4.6, we want to do number 4 through 31 all. And then take a look at 31. 31 you're just going to simplify and come up with a complex number. So in 31, simplify each one and then add them together, and you'll get a complex number. You'll get a real portion and an imaginary portion. Then we're also going to do 37 through through 54 all. That might be it. And then 65 through 70 all. But today, you only need to do this one. So we'll spend 2, maybe 3 days on this. All you need to do today is the first set, 4 through 31 all. All right, get to work.